Okay, those are all, I mean, these are good ideas, a lot of good ideas with this one little simple example. Let's look at better examples. Look at this. Here's a vector value function. This is classic. Hang on, one more before I do the classic new one. Let me say something about this. So this is, what is this? It's a parabola. I guess you could say it's that parabola. It's the most famous, most basic parabola you've ever studied. But here it is in this new chapter 12 language, vector valued functions. Here it is in chapter 10 language, which is called parametric equations. I'm saying they're practically the same thing. I mean, they start to become synonymous. It's just putting those in a vector format. But there is a sort of a difference in the notation. Back when we studied parametric equations in chapter 10, we would do this thing sometimes to clearly see sort of what the path is or what it is. I mean, I figured this out by plotting points and drawing it. But if I didn't want to plot a million points, I could do this thing called eliminate the parameter. Well, I mean, this is real easy and obvious. Listen, if x is a t, can't you kind of replace this t with an x? I mean, if x equals t, I can replace this with an x, and then I have y equals x squared. And I eliminated the parameter t through substitution, right? If x equals t, replace this t with an x, y equals x squared. And this is the good old, what we call, rectangular equation using rectangular coordinates. I mean, you may never even use this language before. I mean, this is just the way you always talked your whole life before you learned about parametric equations and vector value functions. You always talked like this, rectangular equations using rectangular coordinates, y's and x's. Anyway, it's just a parabola. Here it is again in parametric format, and here it is again in vector value function. But sometimes this little trick of solving and substituting helps you see the path. I mean, when the parabola, the rectangular equation, which you're familiar with and you know it's a parabola. You might not stare at that and know parabola. You might stare at that and know parabola is what I'm saying. What about this one? Can you stare at this and tell me what it is? And maybe not yet, maybe not today, maybe not right now. But it's a vector value function, and it's two dimensions. It's two dimensions, so it's in the good old XY plane. I could plot points. I could make a chart and plot points. So technically, I'm plotting vectors. I'm plotting position vectors, which lead me to points. And I could. Do you want to guess? X is cosine, Y is sine. Does that make you think of anything?
Circle.
Circle. Yeah, it is. Yeah, except it's got. Yeah, it's a circle. Radius 3, actually. Maybe this helps. Watch this. Okay, I'm going to play a game here because this is me introducing this topic. I feel like I still. So this is our new way of talking, vector valued functions. If I go back to chapter 10, now see, we could have or would have discussed this in chapter 10. I would have said x is 3 cosine 4t, y is 3 sine 4t. This is parametric equations, plot some points, see what you get. You should have still said circle. It is a circle of radius 3, but I'm about to convince you even more. To really convince you that it's a circle, I think I should kind of eliminate the parameter, try to get to a rectangular equation, and then I'll really prove it to you. So watch what I'm going to do. I'm not really going to solve for t and substitute. Here's what I'm going to do. I'm going to divide by 3. X over 3 is cosine of 4t. Y over 3 is sine of 4t. Now, you see what I just did? Now check this out. What's the most famous identity you know? What's the most famous identity you know?
Sine squared plus cosine squared equals 1.
Yes. Cosine squared plus sine squared does equal 1. So if cosine squared plus sine squared equals 1, then this thing squared plus this thing squared equals 1. So here I go. Using that identity, this squared plus this squared equals 1. Are you guys okay with that? Because this squared plus this squared equals 1, this squared plus this squared equals 1, I've just eliminated the parameter using trig identities. I eliminated the parameter t, and what do I have is a rectangular equation, and what is it? Well, it's x squared over 9, y squared over 9. If you multiply the 9 to the other side, it's this. I did a couple algebra moves in my head right there, but there it is, and that's a circle of radius 3 centered at the origin. And that's what he is, a circle of radius 3 centered at the origin. And that's what he is, a circle of radius 3 centered at the origin. And that's pretty cool, but I wonder what the orientation is. Is it going around clockwise or is it going around counterclockwise? And now maybe I should plot a point or something to see what's going on. Let's, I'll tell you what, let's plot t equals 0. If I plot t equals 0, plugging it in, I guess, what do I get when I plug in t equals 0? Again, I could go here, it's chapter 10. Well, this is chapter 0. Chapter 12. Plug in a 0, plug in a 0. What's the cosine of 0?
1.
1 times 3 is 3. What's the sine of 0? 0. 3, 0. That's the vector. 3, 0. That's the position vector that takes me to this point. I like to erase that position vector, but I'm at that point when t is 0. Sometimes it's nice to make this little note, t equals 0. I mean, you know, t doesn't show up anywhere on here. This is an x-axis, this is a y-axis. We're plotting x and y points, but the parameter t could sort of be just shown off to the side there, like just a little note. I'm right there when t is 0. Hey, what if I plot, watch this one. You ready? I'm going to try something. I'm going to try pi over 2. Let's try pi over 2. So I'm going to do r of pi over 2. Now I'm going to run into a little issue because watch what happens. I'm plugging pi over 2, and this angle's multiplied by 4. This is a quadrupled angle here. So anyway, pi over 2 times 4 is 2 pi. What's the cosine of 2 pi? 1. Times 3 is 3. This is pi over 2, but it's multiplied by 4, so it's 2 pi. What's the sine of 2 pi? 0 times 0. So guess where I am? I'm right back where I started. How long did it take me to go around there? I'm back to where I started, you guys. I'm on a circle, and I went from t equals 0 to t equals pi over 2, and I'm back to where I started. That might be surprising you a tad, but let me just ask you a question. What's the period of this trig function? Do you remember how to do periods? The period of cosines and sines was always 2 pi divided by that coefficient on t. If you remember, the period is always 2 pi divided by that coefficient. So the period for this circular motion here is 2 pi divided by 4. Because of that 4. So what is the period? And what is the period? The time it takes to complete one revolution. So, duh, from 0 to pi over 2, I'm back to where I started. The period of this particular circular motion is pi over 2. Because of the 4. It's been accelerated. A normal, without the 4, what's the normal period? 2 pi, right? Normal period would be 2 pi. But with that 4 there, the period has been shrunk. Yeah. So it's pi over 2. Anyway, I better plot something between there then. I don't know. Pi over 8. Let me try pi over 8. What happens with pi over 8? Let's see what happens with pi over 8. R pi over 8. All right, I'm plotting that. Cool. That's pi over 8 times 4. Pi over 8 times That's 4 pi. That's pi over 2. Cosine of pi over 2.
0.
0. And pi over 8 times 4 is pi over 2. What's the sine of pi over 2?
1.
1 times 3 is 3. Now I am at the vector 0, 3. 0, 3 is this vector, which takes me out to this position, 0, 3. Whew. I'm there when t is pi over 8. By the way, I could have figured this out a little other way. Look at this. What was the whole period to get over here? Pi over 2?
Yeah.
Oh, well, remember I was still trying to figure out orientation. I'm sorry. I think I've got the orientation figured out now. I think it's pi over 8 every quarter of a thing here. Anyway, I think from 0 to pi over 8, I think I'm moving this way. Do you agree?
Yeah.
So I'm putting some little arrows on here. This is counterclockwise orientation. It took me a while to figure that out. It doesn't have to take you that long to figure it out. The truth is, if I was you, I'd memorize this. That if x is cosine and y is sine, it's counterclockwise orientation. That's kind of how a unit circle would move, right? If x is cosine and y is sine, I mean, that makes me think of my trig when I used to pretend x was cosine and y was sine, and I would move around a unit circle like that, counterclockwise. So when x is cosine and y is sine, I would just memorize that rather than calculate. I mean, I just did this to take you through this exercise, plotting points. And what I would really do is I would kind of, at the beginning of the problem, I would make a note of what the period is. That's easy. And then I would make a note that x is cosine, y is sine, so this is counterclockwise orientation. How would you make it clockwise? What if you wanted this problem to be clockwise? Any ideas?
Switch
Swap
it.
I would, yes, good job. I would switch. If x is sine and y is cosine, that does make it go the other way. That makes you have clockwise orientation. It also makes it start in a different place. Although the word start is a little bit of a funny word. What do you think I mean when I say start?
When t equals 0.
Yes. But aren't you allowed to have negative t's before t equals 0?
Yeah.
Yeah. So that's why start is kind of a funny word. But if I use the word start, I mean when t equals 0. If this was flip-flopped, I could get it to go the other way, but it also would start there, actually. It would start there and go this way, instead of starting there and going this way. But those are just things I've learned over the years. I don't know if you have to memorize all this right now. What you should know is when you see x and y, sines and cosines, this is circular motion. Well, wait a minute. It's circular motion when they both have the same radius. What if he's a 3 and he's a 5?
Ellipse.
Then it's an ellipse. Then it's an ellipse. Those are good too. Yes?
What if you switch and negate?
Yeah, that's kind of interesting. In fact, so I asked you, so we spent some time on this guy, plotting some points, and we figured out he has counterclockwise orientation. And then I asked you, after we figured that out, then I tried to ask you, what would it be clockwise? And the truth is, there's several ways to make it go clockwise. I think usually, if you want something to go the other way, maybe replace all the t's with a negative t. I think that makes it go the other way. I'm not sure about that, if that's true for all life. And replacing the t's with a negative t would negate one of these. So leaving these in the same position and negating one of them is another way of making it go clockwise. The one I've latched onto for memorization purposes is when it's cosine and sine, it's counterclockwise, and when you switch them, it's clockwise. But there's other ways to make it go clockwise. So by throwing some negative signs in here a little bit. Let's do this, please. I would like to, here's what I want to do. I want to find and sketch This is a typical test quiz question right off the bat. Find and sketch the velocity and acceleration vectors at t equals 3 pi over 16. Great. Is that what I really want to do? I think so. All right, let's tell you what. All right, I'll tell you what, there's a lot of little things we can do. First of all, how am I going to get velocity and acceleration vectors?
You're going to have a position function to derive or integrate from.
Thank you. I'm going to take the derivative. Right. So let's knock out some couple derivatives. So here I go. The r prime of t is called the velocity, and I want to do a derivative. Anybody know how to do the derivative of 3 cosine 4t?
That's negative
Negative 12 sine 14.
Good job. So you did the derivative of the cosine function, and you did the chain rule, which spit out a 4. Okay, good job. And the derivative of 3 sine 4t.
12 cos 14.
12 cos 4t. Okay, good job. All right, now let's go ahead and do a second derivative, r double prime, while we're got the flow here. R double prime would spit out another chain rule, would spit out another 4, negative 48 cosine 4t. Do you guys agree?
Yeah.
And then positive, oh no, negative 48 sine 4t. All right, cool. So what I have here is velocity and acceleration vectors in general, at any t, which is awesome. I mean, I got these velocity and acceleration vector formulas. Now all I got to do is plug in whatever t they want me to plug in. They want me to plug in 3 pi over 16. But hang on, before I do that, where is my position at 3 pi over 16? I guess I could plug in 3 pi over 16 in here to get my position. I could also do this. If this is t equals 0 and all the way around is pi over 2, what is it halfway around? If that's pi over 2 is all the way around, what's halfway around? Pi over 4? Half of that. Pi over 4. And then what's half of pi over 4?
So you're saying it's going to be negative.
Well, what's half? Hang on, what's half of pi over 4?
Pi 8.
Pi over 8. Okay, so that's that place. Right, that's what this is. This is pi over 8, then here comes another pi over 8. Here comes another pi over 8, another pi over 8. 4 pi over 8 is, yeah, that, right. Pi over 8, pi over 8, pi over 8, pi over 8. So anyway, halfway there is a pi over 16. So there's pi over 16, 2 pi over 16. 3 pi over 16 is this place right here. Right, that's 3 pi over 16. It's a perfect 45-degree angle there, right. But it's technically, it's this point I plotted called t equals 3 pi over 16. And I never did actually plot it. If I plugged it in, I could have got those position numbers. But those position numbers would have been right here. Right. Negative 3 over the square root of 2, positive 3 over the square root of 2, perhaps. Perhaps. Anyway, let's get them here. Let's get these numbers. So I want r prime of 3 pi over 16. Now you don't really need a calculator. I mean, I don't think. Watch. If you plug in 3 pi over 16, the 4 and the 16 cancel, you get 3 pi over 4. The sine of 3 pi over 4 is 1 over the square root of 2. I mean, now I am thinking of my unit circle, which I could think of this circle. It's the sine of 3 pi over 4. It's 3 pi over 16, but multiplied by 4. It turns in, the angle is 3 pi over 4. The sine of 3 pi over 4 is square root 1 over the square root of 2. Or square root of 2 over 2. You want to say it like that? Let's say it like that. Square root of 2 over 2 times negative 12 is negative 6. Oops. Negative 6 times the square root of 2. Cool. Comma. What is it here? It's going to be 3 pi over 16. The 4 cancels. It's 3 pi over 4. It's the cosine of 3 pi over 4. It's the same number. Square root of 2 over 2. Wait a minute. But in that quadrant, cosine is negative. So it's negative, whatever the hell I said. Square root of 2 over 2? Negative square root of 2 over 2. With the 12, it's going to cancel the 12. It's going to be 6 square roots of 2, I think. It might, there you go, dude. That is your velocity vector. Somebody decimalize those numbers. What is 6 square root of 2?
8.485.
8.485. Okay, 8.5 roughly. So here I go. Negative 8.5, positive 8.5. I'm going to draw that from here. Keep in mind that's a 3. Negative 8.5. Hang on, negative 8.5. Well, there's 3, 6, 8.5. Negative 8. And now down. 3, 6, 8.5. Dude, that ain't bad. It's supposed to look like it's tangent to the curve. It's supposed to follow the orientation. If it's cruising this way, you better not have a velocity vector going that way. It better go this way. That's awesome. This is tangent to the curve. This is a beautiful, accurate picture of my velocity vector traveling around this circle. You know, on this particular circle, we're kind of hauling ass. Why are we hauling ass? I mean, it's hard to compare to what, but by multiplying by 4, we shrunk the period. The period is the time it takes to do one revolution. A small period means you're traveling fast. Right. So we got a big, long velocity vector when you're traveling fast. Let's calculate the acceleration at this point. Yikes. The acceleration, r double prime, at this point. All right, well, I'm going to try to do it kind of in my head again. 3 pi over 16, when you cancel the 4, it's actually 3 pi over 4. The cosine of 3 pi over 4 is negative square root of 2 over 2. Times this negative 48 is actually positive 24 square roots of 2. Do you guys agree? Mm-hmm. That's my acceleration. Comma. Same thing here, it's going to be a square root of 2 over 2. That's going to be positive. This is going to be negative 48, so that's going to be negative 24 square roots of 2. Can you make those decimals for me?
33.9.
33.9 or 34. Okay, I'm going to try to do this. At this point, I got to go over 34. Oh my God. 3, 6, 9, 12. 15, 18. Over 34 from that point, and now down 34. Is that what I got to do? Damn it, I can't even do it. Down 34. Are you ready? Tell the maintenance guy. All right, hang on. Now I get to draw that vector from here all the way to that point. All right, here's the thing. I happen to know, so even though, all right, sorry, it went off camera there. Remember, this thing's speeding up, going very fast around here. Whoa, I used the wrong word. It's going very fast. It has a lot of velocity. It has a lot of acceleration. Big, I can't even draw the whole thing to scale here. It does go through the origin. It does. It goes right through the origin. Because it's the exact opposite. It's the exact opposite direction of, of the original position vector. The original position vector took me out there. What was the original position vector? Cosine, sine? Watch this. Look at the acceleration vector. Negative cosine, negative sine. Except it's got 48 on there. See, it's been lengthened but I'm pointing out that it's the exact negative. Negative cosine negative sine is the exact negative of cosine sine. It's the second derivative. It's the exact opposite direction of the position vector. So the position vector took me there. The acceleration vector takes me right back through the origin, past the origin on this case. And there's a beautiful picture. Now let me ask you this. This picture's misleading. Is it speeding up, slowing down, or neither? It's a little misleading. Speeding up, slowing down, or neither? It is neither. It's a little misleading, but this is actually a perfect 90-degree angle. And this is called uniform circular motion. This acceleration pulls it toward the center. It's almost what keeps it in a circle, you could say, although it's almost a chicken or the egg argument. Is it a circle because the acceleration is pulling it toward the middle? Or because it's a circle, the acceleration will be toward the middle? I mean, I don't know which came first, the chicken or the egg, but the acceleration is pulling it back toward the middle, which kind of keeps the particle in this circular motion. If you somehow, if it could get off track, if you shut down acceleration, it would take off and head off in this direction. If you could zero out the acceleration and release it from its path, at this point it would take off in this velocity direction here at this moment. But these velocity vectors are always this long. What is the magnitude of velocity? You could calculate his magnitude if you wanted. Maybe you can see or calculate his magnitude if you wanted. What is the magnitude of the velocity vector? It is the square root of 144 sine squared 4t plus 144 cos squared 4t. Are you guys with me? Do you know what to do now?
Identity.
Yeah, factor out 144 and you're left with sine squared plus cosine squared, which is 1. So now it's the square root of 144, which is the square root of 144, which is 12. I kind of knew that. Again, if you factor out this 12 and pull it out front and calculate the magnitude of what's left, it's just a sine squared and a cosine squared, it's a 1. With the 12 out front, the magnitude's 12. What did I do? Did I calculate this particular magnitude as 12? No, look what I did. I calculated the magnitude of any of my velocity vectors, any of them, at any t. The magnitude of the velocity is always 12. That's what this uniform circular motion is. It's cruising around in a circle and it's not changing speeds. It's not speeding up or slowing down. These are all velocity vectors of length 12. I'm sorry, it's a little short here. But they all have the same length. They're all length 12, no matter where you draw them. All the acceleration is pointing toward the center, and it's not contributing to shortening or lengthening these guys. That's why they're remaining length 12. The acceleration vector is contributing to some change in velocity, though. Not a change in the velocity's length, but a change in the velocity's direction. The acceleration is sort of what pulls it into this new direction around this circle. Right. Check this out. Circular motion's a big one. And like I said, if those radiuses, I had a 3 and a 3 with different radiuses, it would be elliptical motion. Centered at the origin makes it nice. I don't like to off-center them. I like them centered at the origin. Check this out. I got to teach you this for you, Dave. So we've been sitting here with some plane curves. I call them plane curves because they've been 2D. Although when I opened up the scene today, I did mention 3D. Here's a classic 3D vector value function right here. Look at that. Classic, cool, three-dimensional space curve. A curve in three-dimensional space. We can take a derivative of it and talk about a velocity vector. We can take a second derivative and talk about an acceleration vector in space, in 3D space. I can't draw those too well. I can't draw those too well. Really what I want to do is just talk about what this famous space curve is. This is a space curve, and he is famous. You know, if you just ignored the z for a minute, what do you think's going on in the xy plane there?
Circle.
Thank you. Circular motion. Look, x is cosine, y is sine, radius of 2 maybe, right? Good old, so look, in the xy plane, good old circular motion. Now, while it's doing that, and t's just taking me around in a circle, just going around a circle. Now, what's z doing?
Going up.
Slowly rising. So while you're in this circular motion, z is rising, and this is a famous helix, is what this is called. This guy, they're space curves, but this guy in particular is a helix. And we can draw him. Look, I can sort of draw him. It's a helix. It's circular motion in the xy plane, rising up into the z direction. Watch this. I'm going to try to do a circle of radius 2. And here I go. I could plot a point. Look, when t is 0, where are you when t is 0?
Excellent. Right. Up.
2, 0, 0, which is right here. So you kind of start here on the x-axis and in the xy plane, but then as you move, your z is going to rise. I mean, when t is 0.1, your z is 0.1. As you go around this circle, you rise up out of the plane, and you end up right back here, and right above it. How long did it take me to go around? How much time did it take me to go around?
2 pi over 2, which is just pi.
No, the 2 is the radius. It was the 4 that was affecting the period.
Oh, so it's just 2 pi.
Thank you. So it's just 2 pi. Yeah. So it took me 2 pi to go around. So I'm back here, t equals 2 pi. Then down here, t equals 0. Hey, if t does equal 2 pi, then what's the z value here? What height am I at here? What height am I?
No, wait.
Well, it took me t equals 2 pi to get here. So what's my height? What's my z height when t equals 2 pi? 2 pi. You guys okay with that?
Yeah.
So my picture's a little distorted. I mean, that's a 2 and that's a 6. You following me? My picture's distorted. But I'll go around again, watch. And I need to end up right above myself. Go around again if you want. I mean, this goes back. T is allowed to be negative, so it's allowed to go back here. It's allowed to go. It's a helix. All right. So now I'm back in 12.1. So I took you on a little journey. When I started drawing velocity and acceleration vectors and taking derivatives and drawing velocity, I'm up in 12.2 and 12.3. And I'm really anxious to get there. In 12.1, they don't do any of that. In 12.1, you're trying to sketch some curves. I guess you're plotting points. You could use your graphing calculator in parametric mode, but your graphing calculator doesn't help with 3D. So in 12.1, you run into some helixes. Try to pay attention to the circular motion and try to sketch some helixes. Try to sketch some plane curves. There's a couple other space curves. And then there's some weird stuff in 12.1 I didn't get to. When two surfaces intersect, they form a curve, a space curve. Like if I had a sphere, it's a sphere, and I cut it with a plane, oh, this picture's going to be great. Where does the sphere and the plane intersect each other? Jesus. I think there'd be kind of like this diagonal circle here, don't you? Where the plane intersected the sphere. There's like a diagonal circle. And that would be a space curve. And it would be the curve of intersection of these two surfaces. There's some good problems like that in 12.1 that I'll have to get to next class. I mean, I'm running out of time now. So I'm going to quit today. You guys can work. 12.1, 12.2, 12.3.